Okay, well, let's start this last lecture today. It's great to finally also do some teaching. So wonderful segue from Tang's lecture when he finished with the fact that we can do CCP two-step estimation in models with a combination of discrete and continuous choice. Okay. Now I'm going to continue on that theme, but I'm going to take you a step back and go back to full solution methods. All right. So the big idea here is that we want to do, if we want to do a full solution method, say maximum likelihood, a method of simulated moments, we have to solve a model. It's going to have discrete and continuous choices towards at least the middle of the talk. And this is all what I'm going to be talking today about. This is only about the solution. Of course, we're interested in estimating the models, but solution turns out to be also interesting. Moreover, I would say that there's no question about the fact that NFXP is hard to implement computationally. There are two things that we can do. We can have more advanced and sophisticated and smart econometric approach, like the ones that you saw in the lectures today. We could also try to find better algorithms to solve the model. And so this is the lecture on kind of a nice algorithm. How many of you had heard endogenous grid point? A few people. Wonderful. I envy people who haven't, because this is going to be like magic. Okay, this endogenous grid point, it's magic. And it solves a problem which is extremely hard in like no time with wonderful, perfect accuracy. It was developed in macro, so that's why you may not have heard about it, but still. All right, let's dive into it. Motivation is very simple. The combination of discrete and continuous choices is everywhere. How much to work, when to retire, how much to save, when to buy a house, which car to buy and how much to drive. There's, so many questions that actually involved the combination of doing some, taking a discrete decision and then adjusting. And then what do we do in these situations? Well, we have the discrete choice framework, right? And then you have the standard EV errors and all the theory that we've talked so much this week about. We can do continuous choices and estimate early equations and work off the first order conditions. But the combination is kind of rare. Now, why is it rare? Because it's hard. So a dynamic model with combination of discrete and continuous choices involves non-concave optimization, which is just hard. Because first order conditions are not sufficient. Early equations are not going to work right away. We will see that there are kinks in value functions and discontinuities in policy functions. And if you hear this and you are thinking about doing something numerically, you have to be, worried. When the functions that we're working with are not smooth, then like half of the normal methods may not work or may not work well. And so that's what I'm trying to say here. Well, I mean, think about solving a non-concave problem in the Bellman equation if you're going for the full solution. You will have to have an optimizer that would have to somehow be able to find a global solution, and that's definitely not guaranteed. So endogenous grid point to the rescue. What does it do? Let me start with that screen doesn't work. That was actually so useful. Okay, I'll be looking at my slides here. I want to talk about the original EGM, endogenous grid point method. It was introduced to economics for a very particular problem, the problem of consumption and savings in macro and all the stochastic growth models, buffer stock savings models that are fall into the same framework. I came to this trying to work on a retirement problem where consumption and savings decisions were very important. And so it's kind of naturally, I needed the discrete part of it. And Bertel kind of even earlier worked on the problem with entrepreneurship where people had to accumulate some assets before they switched from like paid work to entrepreneurship. So, think about structural labor today or right now. I don't think it's been applied to games, but I think it's totally applicable if we think a little bit harder. So I want to extend this EGM framework to models with discrete choices, and it's going to be nasty and scary. And then we take a next step, or one step further, and try to do something with this problem to make it more tractable. And well, surprise, surprise, hidden taste shocks really helps. And I'll talk about that. And then finally, kind of the biggest question for usability of this approach is whether you can have more complicated models to be solved with the same tricks. And this is where I want to talk about multidimensional extensions. So models with multiple continuous choices, whether we can use something similar and how that would be done. But you know, the point, if you fall asleep now, which I hope you don't, is that this is so good that if your model somehow fits into this framework, this is way better for solution of the model than anything around, anything else. Wrong direction. Right, so what is the EGM? This is the method of endogenous grid points. It's a fast method for solving a very particular problem. It applies to both finite and infinite horizons, even though I'm going to be talking about finite horizon just for simplicity. It requires strictly concave and monotone utility function. Differentiable is also good. We will want to be able to analytically invert the marginal utility function. Okay, so think of log consumption or Sierra array specification, where the marginal utility is going to be monotone and invertible. We will first look at one continuous state variable, and this is wealth, or you know, size of the cake if you're thinking about the cake eating. One continuous choice, consumption, and then that's it. This is going to be a very simple setup. And we will have a normal, very natural way to set up the laws of motion of these variables, of this variable. But that's kind of to keep in mind to understand why it works. It will accommodate binding credit constraints really, really well. And that's also generalizable. Wrong direction. All right. When we go to the discrete continuous EGM, the main assumption on the utility function will remain. We will allow here for additional discrete states with the assumption that the transition probabilities will be independent of this special state variable M, and still will have one continuous choice and allow for one discrete choice variable, but this discrete choice can encode as many as you want of different discrete options. Right, and there will be two flavors. The setup without the taste shocks, and then the one that includes the taste shocks makes the computations much more pleasant. Yeah, learning outcomes. If your model has one continuous consumption and additional discrete choices, you got to use this. As I said, that's the best method or approach in existence. Why is that? Well, this approach avoids all root finding operations. And if you think about how to solve a dynamic programming problem with continuous choice, you know, we would have to search for the optimal decision within the Bellman equation. And if the choice is continuous, well, that's a complicated iterative process, right? You have to search for the optimal action for each point in the state space. So do it many, many times. And this is equivalent to root finding. You can think of this as solving an equation for first order condition. Now, EGM doesn't need to do this. And that's the reason why it's so fast. Now, if utility is separable in continuous discrete choices, then DCEGM will also be very efficient with credit constraint. And I put a star here because, well, credit constraint in a consumption savings problem, but it might be something different in more general formulations. And as I said many times already, extreme values will help. Okay? Is this the direction? Start with EGM. Standard plain vanilla. Let's just jump into the model. Bellman equations, you've seen so many times. This is your standard consumption savings problem. One state variable M, I'm choosing C consumption level between 0 and this amount of money that I have, utility of consumption, and the continuation value. You can see that there's nothing in this model. My tomorrow's amount of money is just the interest plus whatever or times whatever I saved. I'm going to treat everything as deterministic to start with, and then we can talk about what happens when the returns are stochastic. You know, when you're doing empirical work, don't forget -1. It represents the same preferences, of course, but if you're trying to estimate this raw, you don't have -1, then everything jumps so far, you know, to out of place. But this converges uniformly very nicely to log. Okay, what's the solution to this simple consumption savings problem? It's analytical. It's right here. Right, I'm not writing the formulas for this case constants, but you can see that the value function is well, it has this form, right? And it approaches log with some scaling coefficients, and the optimal consumption rule is linear in M, in the level of wealth. This can be just shown analytically. All good. And just to make sure that we're on the same page, you know, this was set up. Well, I guess, you know, I'm explicitly not saying whether this is finite horizon or infinite horizon, right? A little bit sloppy. But if I'm thinking about the finite horizons, then I will find this whole collection of value functions for different time periods and a whole collection of optimal choices, right? Optimal policy functions. And you will tell me immediately where's the solution for the infinite horizon problem. Should I do cold calls? Well, think about how you would solve an infinite horizon problem doing backwards induction. You start with some guess of the value function, and then you iterate on the Bellman equation. I'm thinking that we're doing VFI, right? And we will get a next kind of next approximation of the value function, and then they should converge, right? In the single agent problem, we know that there is a single solution. They will converge. They will converge to something here, and the same thing in the policy space. You know, you can see that convergence kind of happens towards this line here on the bottom, right? So I can solve the finite horizon and infinite horizon problem with this approach in the same way. All right. Let's complicate the model and introduce some random income, or maybe it will be deterministic for sometimes. So the only change is that this y, right, that is added to consumable wealth in every time period. And so this is where it's going to enter. Suddenly there is no analytical solution, and we have to solve it somehow. So what can we do? Let's do backwards induction. You know, start with value function iterations. This is something that you've learned in the first day that we should not do, right? What do we do instead of value function iterations? Say again? Policy, yeah, when Newton-Kontorovich, right, which is much faster. But let's start with simple stuff. So if I want to do value function iteration, well, that means that I need to solve the Bellman equation on some on the state space, right? The state space is given by a single variable here, the wealth. But let's discretize it. Since we're working on the computer, let's just treat it as a discrete variable. So that's very standard what people actually do. We put a grid on this state variable M. And that's kind of like the first step, which is implied. And so now I have this collection of points of the state space. And I have to solve the Bellman equation in each point, right? Are you with me? In the terminal period, this is just going to be a maximization of the utility function. In all other periods, you know, the maximand in the Bellman equation will include the expected value. You know, this talk is very much down to earth. Like, we are computing, like imagine that we are writing code. I will show you code as well. So the Bellman equation is, you should think of like coding it up. So we're solving this maximization problem. And now if C is continuous and we want to treat it as a continuous variable, then that's what I was saying. This is a non-trivial problem to solve. We will have to do some quasi-Newton or Newton methods or solve an equation for first order conditions, something like that. All right, well, let's see. Let's look at the code. This code is in the repository. And let's see, where is it? You'll find it under this lecture 8. In the code directory, you can see there's MATLAB and Python. They're not equivalent. I'm going to run examples from MATLAB, but Python has also a very good implementation of the whole thing as well. Now, in MATLAB, I'm going to use my trusty VS Code editor. So just to just give you some understanding of what's happening here, I'm using this little blocks of code to run different examples. And so this if1 that's going to run this little code. But in order to set up the model, I'm calling this function, right? This is the use of MATLAB with to create objects. It's object-oriented programming in MATLAB. I don't know if anybody does this, but this is going to create a model which has all the properties and various methods, specifications of utilities and things like that. And in particular, it will have a solver here called solve VFI. And what it does is essentially what I went through. Sets up the grids and then has this Bellman maximand. It's called Bellman, but it's really maximand, and calls the main step here is basically here, right? It calls fmin unc in each point in the state space in each time period. So it solves a lot of optimization problems. Okay, so let me run this. I'm going to run this block here. And I like to run my MATLAB from terminal. This is also MATLAB here. Let me make it a little bit bigger. So if I run, yeah, you can see here's my model, and I'm plotting it out every time a point is solved in the state space. This is the state space. There's 25 time periods. Okay, this comes up every time it plots the first time, and here's my solution, right? I mean, this is not a very slow computer. In fact, it used to be that I could speak a little bit more while it was doing 25. Maybe I can increase the Tmax now to have a little bit more time. But here's the solution, right? And you can try it yourself. I encourage everybody to play with the code. Again, there is a Python version as well. Let's remind ourselves of the early equation. Victor set it up already on the second day, first day. We can write down the first order conditions for the Bellman equations. Of course, in this simple model, it's going to be extremely simple. And then the envelope condition for the derivative of the value function itself. And notice that this expression that we get in this particular case is just identical, right? That's because of the functional form of this intertemporal budget constraint. What we have is that the derivative of the value function with respect to wealth is exactly equal to the derivative of the utility function evaluated at the optimal choice. So at CT, which solves the first order condition. And we get the familiar expression for the early equation, which will play a key role in the whole talk of the EGM. So what do we have here? We have an equation that connects the optimal choices of consumption in 2 consecutive periods. Okay, so it says that the marginal utility of optimal consumption today has to be equal to this expression of the marginal utility of optimal consumption tomorrow. Of course, assuming the interior is solution for now. We can use early equation to solve the problem, to run backwards induction as well, right? We could also fix a grid over M, and then instead of maximization problem, we could solve the first order condition in each point of the state space in each time period. This approach has the same complexity, essentially, solving a nonlinear equation. Okay, well, finally, EGM. imagine a world in which we don't have to do this optimization in each point of the state space. It's pretty obvious why it is, it is not the easiest approach. And so can we just avoid numerical optimization altogether? Here's the idea. This is the main idea of the whole method. Instead of searching for the optimal decision in each point of the state space, that's what we've been doing so far. Let's look for the state space, value of the state variable. So level of assets, where some decision will be optimal. Okay? That's the key. So I don't want to search for the optimal decision in the fixed grid on the states. I want to guess a solution and find the point in the state space where this action will be optimal. And that's what creates the endogenous grid. All right, let's, do you understand the idea? It's kind of turning the optimization problem inside out. Let me go through the steps. So let's assume that this is finite horizon and there's no bequest, right? So it's optimal to just consume everything you have in the final horizon. Doesn't have to be this easy, but let's start with a simple case. Now, the first action, this whole box here is what we can refer to as EGM step. We will do this many times. But in one step, I want to get some value, which I will call A, and I think of this as the end of period asset. So this A is something that I'm left with in the end of the period after consumption. So, right, so we remember this is like M minus CT. That's what we're left with. And these values of A, they will come from some grid. We can fix it and then use the same one over and over again. We can make it time specific, or we can make it adaptive according to some other rules as well, which sometimes proves to be very a useful idea. Now, given A, can I calculate how much money I will have tomorrow? Well, with this simple intertemporal budget constraint, yes, I can. It's just R times A, the gross return times the A, right? Now, imagine that by now I already know the policy function tomorrow. And in capital period, I do. And then, doing backwards induction, I will know the optimal consumption function one period ahead. And that means that I can put this MT plus 1 into my consumption function and find the optimal consumption level in T plus 1. Okay? That means that I can plug it into the early equation, into the right-hand side of the early equation. And here's the assumption on the analytical invertibility of the marginal utility. If I can compute this, the inverse of the marginal utility of that right-hand side, then what I get is exactly the optimal choice, optimal consumption today. Okay? And look what happened. I started with some guess of the end of period wealth, and I got the optimal level of consumption that goes together with that guess. That is a function of that guess. Okay, what's left to do? I just put them together, this A that I started with and the computed optimal level of consumption, and that gives me my point in the state space where that guess A corresponds to the optimal consumption. And so this is how we turn this function, this whole process inside out. I'm starting with some, arbitrary number, and I apply the inverse of the early equation and already computed on the previous step policy function tomorrow to calculate the level of asset today, MT, where this guessed end of period wealth and the level of consumption are in fact optimal. And now I can repeat this box for many different A's. Okay, I can go through many different levels of end of period wealth. And essentially what I construct is this pairs of MT and the CT. I can construct, right, a table of wealth and the corresponding optimal consumption for many, many different gases of A. And then I can interpolate this table, and that would be a representation of the optimal policy function today. And that means that I can go back to the previous periods in my backwards induction procedure. Does it make sense? Everybody is on board with me? So look, we completely avoided optimization. So now
Can be parallelized, no?
you can parallelize over A, absolutely. They're completely independent. So this is a good way to think about this. You know, given the early equation, we can express these pairs of consumption and the and wealth, or should I say levels of wealth and the corresponding optimal consumption as a parameterized curve, where A is a parameter. So by shifting around this A and plugging it into these two formulas, what I get is the pairs of numbers that describe the policy, the optimal policy. As you can see, if I have analytical inverse of the utility, which a lot of the times we do, this is just direct computation. Very cool. So that's the magic that I've promised. Do you think it's hard? No, it's not. So 11 lines, this is very old MATLAB code, which solves a dynamic stochastic consumption savings problem. You know, with quadrature points, so we're calculating the expectation. This is, I think this is the random income. I mean, this is a serious problem. This is something that is not like a simple trivial example. Here are runtimes. I'm comparing to this earlier solver done in backwards induction, right? So time iterations. You can parameterize the problem such that, you know, EGM is insanely fast, or much, much faster, insanely faster. But in the same time, look, we're solving an early equation. And the traditional measure of accuracy in these problems is the early residual. So how much the early equation does not hold. And you can see that, I mean, that basically gives foundation for these numbers. We're extremely accurate. So by solving the early equation directly and kind of recovering the solution directly from the early equation, you're guaranteeing that the problem is solved very accurately as well. So it's both very fast and very accurate. Let's look at the code. Any questions so far? I mean, the first time I saw this, you know, EGM step thing, it's kind of clear, but then it's kind of magic. You don't believe that it works. Let's see. So I want to run this thing here. Oh no. Oh no. Hide everything. Okay, did you see that? I should run it again. Now, how you think it's only one time? No, it solved it 100 times. So the runtime for one solution is 2,000. So I mean, it's so fast, it's very inaccurate, right? Like it compares this calculation is affected, but by everything else that goes on my computer right now. Yep. So everything hinges on the early equation, right? And so this expectation, as long as you can compute the right-hand side of the early equation with whatever uncertainties that are in the model, then it will work. Of course, you're losing accuracy when you're computing the numerical integrals. I would have to look at the early equation, but I don't see why not. If we can put it on the right-hand side of the early equation.
One question, so can you apply this to the utility?
So the condition is the invertibility of the marginal utility.
But if you,
So what sort of non-continuous utility?
so you have key in utility. How do you?
The question here is whether you can compute this efficiently fast. And I guess with kinks in the utility, there's a question of existence, right, of solution to this equation. So the marginal is going to be discontinuous, and whether in general, maybe not, but it could be possible depending on the structure of the problem.
So you have key, you can actually divide it.
Yeah, divide utility into two regions and try to solve this equation somehow. Yeah. Yep.
I don't understand the EGM of like operates faster, but also the intuition of better performance.
Better performance in terms of accuracy.
Yes.
Well, we are solving early equation directly. Whatever EGM computes, all these pairs of points solve the early equation. And the early equation is the measure of accuracy, right? That's the characterization of the optimality in this problem. So it's almost like we're assuming the result, right? We're using the criterion of accuracy to solve the problem. Well, but why not if we can? Okay, that was the main idea. Let's now try to build on it. So credit constraints. It turns out that if the utility is monotone and concave, so not strictly, I think this is enough to have monotone, but maybe I should discuss with Tang. We can show that this end of period asset is non-decreasing in wealth. So A is a non-decreasing function of M. It can be discontinuous, but it's non-decreasing.